For our physics media project, we chose the topic simple harmonic motion. The objective of our project is to demonstrate simple harmonic motion through the strings of a guitar. What is simple harmonic motion? Simple harmonic motion is movement through an area at equilibrium. Equal forces are acting on each side of the middle point, and it utilizes Hooke's law. Simple harmonic motion also assumes that no other resistance, such as friction, air resistance, or dampening, are affecting the object. In simple harmonic motion, the oscillation of the object in question results in the sine or cosine function being produced from its movement patterns. Measurements originating from the equilibrium point, 0, result in a sine function being produced. And measurements originating from a non-zero or maximal point results in a cosine function being produced. A real-life example of simple harmonic motion is vibrations from sound waves entering the ear causing the oscillation of a membrane in the cochlea. The vibration caused can be modeled as a mass on a spring. The period of oscillation of a segment of the membrane depends on the mass, which is the thickness of the membrane, and stiffness, the rigidity of the membrane. Our experiment will use a guitar string to demonstrate simple harmonic motion. How does simple harmonic motion work on a guitar? A string is in equilibrium and is plucked. The force created by plucking the string creates a transverse wave that travels up and back down the length of the guitar. The energy dissipates in the form of sound. Since the energy slowly dissipates into sound, the string eventually slows down until it returns to equilibrium. The function used for simple harmonic motion is x equals a cosine of omega times t, or x equals a sine of omega times t. X represents the position of the object, a represents the amplitude, omega, which is equivalent to 2 pi times the frequency, represents the natural frequency, f represents frequency, and t represents time. Our prediction is that the graph produced by the plucking of a guitar string will be a sine graph because the string starts at the equilibrium or 0 position. String 1 of the guitar. String 2 of the guitar. String 3 of the guitar. String 4 of the guitar. String 5 of the guitar. String 6 of the guitar. Now here is a slow-mo of the first string of the guitar. As you can see, the guitar string starts at the equilibrium or 0 position. After it is plucked, it starts to oscillate up, which is the positive position, and down, which is the negative position, at a constant rate. This creates the sine function we see in simple harmonic motion. Because of other factors such as air resistance and absorption by the guitar strings, however, the oscillation eventually stops. In conclusion, out of the 6 strings on the guitar that were strummed, the strings with the greatest diameter produced the lowest frequency. This is a result of the oscillatory frequency being lower than that of the strings with a lesser diameter. Therefore, the conclusion that can be drawn is that the size of the string is inversely proportional to the magnitude of its frequency or oscillation.